Hello, my name is Novindra Chonglagai. I am a student at TIHA Clone, currently studying Integrated Water Resource Management. Imagine waking up in Bonn, turning on the tap and filling a glass of drinking water. For us, this movement feels simple, but behind that glass of water is a complex system of abstraction, transportation, and treatment. Today, I'll take you on a journey through a Bonn's drinking water supply system from the water source to the household tap. I'll also discuss the current situation, the main challenges, future plans, and how artificial intelligence could support the system. Bonn is home to around 330,000 people. Together, they consume around 22 million meter cube of water every year. To deliver this water safely, several organizations work together. The Wadbak Talisparabendhan, known as WTV, is responsible for mass abstraction, treatment, and the transportation of water. Whereas Stadtwerk Bonn supplies the water to the consumer, while Bonn Nets operates and maintains the local distribution network. So when someone in Bonn opens the tap, water have traveled through a large regional system. The features of Bonn water supplies is that it does not depend only on one source. Instead, it uses three different sources. The first is Wanbach Reservoir. This is the major surface water source with a storage capacity of approximately 41.3 million meter cube of water. Water is pumped from the reservoir area to the Zigbal-Zeigel treatment plant. Water is treated there. Around 28.1 million cube of water is abstracted annually. The second is the Hennef groundwater systems, located near the confluence of Zig and the Brine River. Here, four horizontal filters wells abstract 20 million meter cube of water every year from the sand and gravel aquifer. The groundwater is naturally influenced by a bank infiltration, rainfall infiltration, and the recharge from the surface water. The third is Mindroof Waterworks in St. Augustine Mindroof. This groundwater source was developed to support the Bonn's drinking water and uses two horizontal wells. It can provide up to around 7 million meter cube of water per year under the current permit. Together, these three sources provide a total license abstraction capacity of around 55 million meter cube of water per year. This diversity is extremely important. If one system becomes temporarily unavailable, the other two can help and maintain them. The reservoir or the groundwater well cannot simply be sent directly to our taps. It must pass through a careful controlled treatment process. For reservoir water, the process begins with flocculation, and water goes through deacidification and then passes through quartz sand filters, which removes the fine particles and remaining impurities. After filtration, the pH is corrected using a lime water. Finally, chlorine dioxide is added for disinfection before the water enters to the distribution network. Groundwater normally needs less treatment because it already has a relatively low concentration of iron and magnesium. However, it is still continuously monitored to ensure that extraction remains sustainable and that the quality remains safe. After treatment, the water begins its another important part of its journey. WTV transport the water through around 230 kilometers of bulk transmission pipeline. The system includes three main supply lines, pumping station, elevated reservoir, and three Rhine River crossing. At Tubewell handover station, the water is transported from WTV to Bonn Nets. From here, it enters to the Bonn's local networks. Inside the city, the water travels through roughly thousands kilometers of mains and reaches around 60,000 households. Every reservoir containing 15 storage chambers provide an important buffer during the period of high demand. In addition, 15 pressure station helps to ensure that water reaches every customers in different parts of the city at a suitable pressure. At present, Bonn has a highly reliable water supply system. There have been no supply failures since WPTV began its operation. The system also follows a strict German and European drinking water requirement. Water quality is measured, is monitored through source protection, treatment controls, and regular sampling. The public network has also been modernized, with the lead pipe removed from the public system since 2013. Another positive development is the use of photovoltaic panels on the earth cover reservoirs. This shows the water supply is not only about delivering the safe water, it is also increasingly connected to the renewable energy and the climate protection. However, even a reliable system must prepare for the future risks. The first challenge is the climate change. Hotter summers and longer droughts can reduce water availability, while increasing demand. In 2020, peak delivery reached around 47.9 million meter cube of water, which was close to the license capacity. The second challenge is the aging infrastructures. A network of thousands of kilometers require a continuous inspection, maintenance, renewal, and leak control. A, a small leak may not be visible on the surface, but over time it can result a significant water loss. The another challenge is energy use. Pumping and treating water requires electricity. Therefore, Bonn goals becoming more carbon neutral will require a greater use of renewable energy and more efficient pumping operation. Finally, new contaminants such as pharmaceutical, microplastic, and PFAS may require improved monitoring, and it in some cases also need the additional treatment process. This is where the artificial intelligence could become a valuable supporting tools. Imagine that sensors are continuously measuring pressures, flow, sound, water quality, and the reservoirs level. AI could analyze this information much faster than a human operator can do it alone. For example, an AI system recognizes an unusual pressure pattern and warns the operator about a possible leaks before the pipe outburst. Acoustic sensor could help to locate the small and underground leaks that are difficult to find using a traditional method. AI could also support water resource planning. In treatment plant, AI could analyze real-time water quality data and identify the unusual changes. It might detect early signs of pollution or predict a runoff event before contamination of water. Contaminated water is the treatment process. AI could also optimize the pumping and storage. When renewable electricity is available, the system could pump and store the water more efficiently, reducing both energy consumption and operating cost. But AI is not a magic solution. It can also produce false alarms, depend on the biased or incomplete data, and create a new cybersecurity risk. So the next time we open the tap in Bonn, we can remember that the water has traveled through a carefully coordinated system. Bonn's water system is secure today because it combines different resources, strong infrastructures, careful monitoring, and cooperation between the several organizations. The future challenge is to make this system even move towards the water supply system that is not only reliable but also more predictive, efficient, sustainable, and prepared for the future. Thank you for watching.